Okay, with just linear collisions, you'll find that the momentum is always conserved. Okay, so one mass flies in, hits another mass, and they both move off afterwards. Total momentum before equals total momentum after. Same thing happens with collisions where the masses head off in different directions. This is called two-dimension collisions. And what we find is that the horizontal momentum is conserved as well as the vertical momentum. And in this case, the vertical momentum is actually zero. So zero vertical momentum here, there must also be zero vertical momentum afterwards. In other words, the momentum of A cancels the momentum of B in the vertical direction. To solve, we could do two things. One is we look at the total horizontal momentum before equals total momentum after, or we could look at the vectors. So to solve using vectors, the vector 1 coming in here must be equal to the 2 added up afterwards. Okay, so final one of P1 and the final of P2 will give us the initial P1 added together. Method 2, using components, the total momentum horizontally can be found beforehand. In this case it's just M1 V1 because this was equal to 0. And that gives you the total horizontal momentum before. And that must be consistent afterwards. So this value here, which is the same there, is equal to the same horizontal components of these two, that component and that component, added together afterwards. And then the total vertical momentum beforehand, which is 0 because it's not going up and down at all, so there's no up or down motion here. That is going to equal the total over here. So the component going up there must be equal to the component going there. In other words, they must cancel out. I'm actually missing something here. I'm missing the angles. Okay, so theta, phi, theta, phi.